Hi everyone, in this video we're going to look at network monitoring. So in order for us to know about network monitoring, it's important that we understand some of the network characteristics that we are monitoring. So what we monitor is basically depending on the nature of the organization, and the significance and relevance of network characteristics vary with applications. For example, the nature of the organization. A content distribution network may be interested in measuring latency from its clients to the application server. So take note here, the network characteristics that is of interest to be monitored is latency, because we do not want to have a high latency when our business model is about content distribution to the client. So another example is a load balancing application. So we want to measure available bandwidth because this available bandwidth will be the parameter where we may adjust our load on the servers. Some other network characteristics are congestion, queuing delay, network failure, topology discovery, and also bottleneck determination. In this chapter, we learned that there are 4 network characteristics that constitute the basic paradigm of network measurements. So that means this is the main 4 network characteristics that is very important. Once we measure these 4 network characteristics, we are able to get the other network measurement parameters. So the 4 main network characteristics are latency, packet loss, path detection, and also bandwidth. Let's look at the first characteristic, which is latency. Latency refers to the time taken by the message to traverse from the sending host to the destination host, and is usually measured in milliseconds. So sometimes how this latency characteristic is used is when we measure the latency or the time taken to reach some servers, and we compare between the two parameters to measure the availability of this server. So in the case of the content distribution networks just now, we want to select the content distribution server which has the lower latency. So from the parameter of the latency, we are able to monitor the variation in latency, or the other name is called deviation. By measuring the variation or the deviation, we can determine the quality of the path, and we can detect network congestion. The next characteristic of the network is packet loss. We can see that the network is experiencing packet loss if the rate of packets sent from the source host is not equal to the rate of packets received at the destination host. So it is calculated in percentage, which is the rate at which packets are being lost while traversing through the network path. A high packet loss rate means a low performance. The next characteristic is path detection. So this is the process of determining the actual path taken by the message in reaching from source to destination. So we understand that when a packet traverses the internet, it will go from router to router, and at each router, there will be path determination by looking at the dynamic routing protocol. Since there are many possibilities for a path from one host to another, path detection enables an application to determine the actual path taken by the message during the transmission. Path detection may also be used to isolate network failure. The fourth network characteristic is bandwidth, which refers to the capacity of the path to transfer data in a unit of time, and it is measured in bits per second, or BPS. So in business models, for example, multimedia applications, bandwidth takes a very high role in determining the best available path. If the available path has limited bandwidth, then the multimedia application will suffer degraded performance. Now that we've looked at the network characteristics that we want to monitor, let's look at the types of network monitoring. In general, for this syllabus, we categorize the network monitoring into active and passive monitoring. So active monitoring involves injecting probes in the network specifically for the purpose of monitoring. That means we are adding additional packets into the traffic for measuring the network characteristics. So in this case, we might be adding some overhead, but it is for an advantageous purpose, which is monitoring the network traffic itself. Under normal circumstances, this additional traffic that we are adding is usually relatively small compared to the actual capacity of the network. So therefore, the cost of injecting additional traffic is very minimal. Since we are the ones adding the additional traffic into our network, we are able to control the interval, the packet size, and also the path. On the other hand, passive monitoring simply refers to the process of observing the existing network traffic. So based on our observation, we collect information without injecting additional monitoring probes into the network. So we need to be able to read the actual packets in order to retrieve the information. Packets are captured by monitoring the application, which is deployed either on the source and the destination host or along the path through a tab. The preference for the type of monitoring varies with the application. For example, the passive approach are used in intrusion detection systems, while the active approach are used in load balancing systems. We can also employ a combination of both passive and active schemes for higher efficiency. So in the slide, this is an example. There is a RAN grid monitoring system. This is an industry-based monitoring system from RAN Industries in the UK. So they deploy both passive and active monitoring. One, we use passive mode when an application is sending messages. That means they do not add additional traffic packets. And then they use active mode when the application is silent because they cannot gather any information when there are no messages being sent. So they inject additional traffic packets in order for them to be able to monitor the packets or the traffic. So for passive monitoring, since we do not add any additional packet, there is no choice for measuring the information. We need to use whatever protocol that is being used for sending all the traffic. But in the active mode, since we are the ones adding additional traffic packet, we need to decide about the underlying protocol to be used for sending these monitoring probes. So the protocols involved are ICMP, TCP, and UDP. So this is basically a refresher about these protocols. You may have encountered these protocols in other courses. The first one is ICMP, or it stands for Internet Control Message Protocol. So basically when we use the ping command, we are using the ICMP. So ICMP is actually an assisting protocol for the network or the internet layer. So it also operates at the networking layer. So ICMP-based schemes do not require connection setup or handshake. Just the same as Internet Protocol, which is connectionless protocol. ICMP is also a connectionless protocol. They also do not require any specific implementation at the recipient end. For example, only the host sending the active probes implements a mechanism for sending the ICMP probes. So when using ICMP as a network monitoring tool, we need to be careful because when we use ping, if there is a continuous ping, it may cause buffer overflow because when we send a ping, the destination host should automatically send a reply. So if we send continuously, that may cause buffer overflow at the destination system and also may cause the destination system to crash. This is why some organizations, they block the ICMP messages. Next is TCP or Transmission Control Protocol. So this is at the transport layer, and this is the main transport layer for internet applications. So TCP-based utilities bear the overhead of the TCP handshake. That means TCP is a connection-oriented protocol. Before sending any data, they need to be having a connection establishment phase between the sender and the receiver. TCP-based tools also require that the destination host runs a service on a designated port. The sending host establishes a TCP connection to the destination through the TCP handshake and sends probes to the destination host at the server port. And then the server will reply with a response that is used for the network measurement. An important limitation of the TCP-based tool is that since TCP is not a packet-based protocol, it makes its own decisions about sending packets. So TCP has its own congestion control algorithm, such as Nagel's algorithm. So it will gather all the packets into a maximum segment size before sending because it doesn't want to have small bytes in a packet and cause congestion. The next protocol that can be used for active monitoring is UDP or User Datagram Protocol. This is a datagram-based protocol that operates at the transport layer. And unlike TCP, UDP does not require a handshake. And UDP has a small overhead because its header is only 8 bytes as compared to the TCP, which has 20 to 40 bytes of header. So unlike TCP, which may adjust the packet size, because of the congestion mechanism, UDP is a packet protocol like IP, so we can send probe packets at control intervals. So in terms of network management, network monitoring is a critical IT process where all networking components like routers, switches, firewalls, servers, and virtual machines are monitored for fault and performance and evaluated continuously to maintain and optimize their availability. So network monitoring in a company or organization should be done proactively. That means we should prevent something from happening rather than we do something after the event has happened. Finding performance issues and bottlenecks proactively helps in identifying issues at the initial stage, and efficient proactive monitoring can prevent network downtime or failures. Let's see some important aspects of network monitoring. The first one is monitoring the essentials. In effective network monitoring, the first step is to identify the devices and the related performance metrics to be monitored. The second step is determining the monitoring interval, and devices like desktops and printers are not critical and do not require frequent monitoring. On the other hand, servers, routers, and switches perform business critical tasks, but at the same time have specific parameters that can be selectively monitored. Next is to optimize the monitoring interval. Monitoring interval determines the frequency at which the network devices and their related metrics are polled to identify the performance and availability status. Setting up monitoring intervals can help to take the load off the network monitoring system and in turn your resources. So the correct interval depends on the type of network device or the parameter that is being monitored. The availability status of devices has to be monitored at the least interval of time, preferably every minute. CPU and memory statistics can be monitored once every 5 minutes. The monitoring interval for other metrics like disk utilization can be extended and is sufficient if it is polled once every 15 minutes. Next, we need to select the right protocol. When monitoring a network and its devices, a common good practice is to adopt a secure and non-bandwidth consuming network management protocol to minimize the impact it has on network performance. Most of the network devices and Linux servers support SNMP or Simple Network Management Protocol and command line. Windows devices support Windows Management Instrumentation or WMI protocol. SNMP is one of the widely accepted network protocols to manage and monitor network elements. And most of the network elements have already come bundled with the SNMP agent. All you need to do is enable and configure the SNMP elements to communicate with the Network Management System or NMS. Next is setting thresholds. Thresholds are used to identify performance bottlenecks proactively, and thresholds limits vary from device to device based on the business use case. Configuring thresholds help in proactively monitoring the resources and services running on servers and network devices. Having looked at all the elements of network monitoring, you as a network administrator need to design a network monitoring strategy. A network monitoring strategy consists of tools and techniques to analyze and measure network performance. This strategy examines how your company monitors and interprets the performance of a network. And this includes what performance metrics you look at and the actions your network team takes to establish performance-related fixes. Network monitoring systems include software and hardware tools that can track various aspects of a network and its operation, such as traffic, bandwidth utilization, and uptime. Here are some network elements that may be critical for you to monitor. The key benefits of network monitoring include clear visibility into the network. Through network monitoring, administrators can get a clear picture of all the connected devices in the network, see how data is moving among them, and quickly identify and correct issues that can undermine performance and lead to outages. It also leads to better use of IT resources. Using hardware and software tools in network monitoring systems reduce manual work for the IT teams. They also help to gain early insight into future infrastructure needs. Network monitoring systems can also provide reports on how network components have performed over a defined period. By analyzing these reports, network administrators can anticipate when the organization may need to consider upgrading or implementing new IT infrastructure. By using network monitoring tools, we can also have the ability to identify security threats faster, and network monitoring helps organizations understand what normal performance looks like for their networks. When unusual activity occurs, such as an unexplained increase in network traffic levels, it's easier for administrators to identify the issue quickly and to determine whether it may be a security threat. In modern network monitoring tools, we also use some form of automation. These systems are designed to trigger events when network data falls outside set parameters, therefore functionally eliminating the middleman and improving response time for network errors. Here are some of the more common general techniques used to collect data for monitoring software. One is pink. The second is by using the SNMP or the Simple Network Management Protocol, where we monitor individual devices in a network through monitoring software. Next is by using syslog, which is an automated messaging system that sends messages when an event affects a network device. Administrators can also deploy scripts, which are simple programs that collect basic information and instruct the network to perform an action within a certain condition. Let's look at the SNMP or Simple Network Management Protocol. This is an Internet Standard Protocol for collecting and organizing information about managed devices on IP networks and also for modifying that information to change the device behavior. The well-known ports for SNMP is 10161 and also 10162 for any traps. SNMP operates at the application layer, and the specifications for this protocol can be found at RFC number 6353. So SNMP works by sending messages called Protocol Data Units or PDUs to devices within the network that also supports SNMP. Using these message requests, the network administrator can track virtually any data values that they specify. The next tool that can be used is syslog. Syslog simply sends messages to a central location, for example, a syslog server, when specific events are triggered. Syslog is a great way to consolidate logs from multiple sources into a single location. Most syslog servers have a couple of components that make this possible. One, a syslog listener. A listener process gathers syslog data sent over UDP port 514. UDP messages aren't acknowledged or guaranteed to arrive. So syslog may use TCP to ensure message delivery. A syslog server also needs to have a database to store the syslog data, and there may also be a need for management and filtering software so that we can monitor and filter important log messages. There are certain limitations for syslog. For example, the syslog protocol doesn't define a standard way for the message content to be formatted. So there are many ways to format a message, and some of these messages do not relay any useful information. And also, since syslog uses UDP, some of the syslog messages may not be guaranteed to arrive. There are also no authentication mechanism for syslog, so it may pose some security challenges. You may refer to these references for further information.